Hello everyone and welcome to our new section which is called AVL Tree. With this lecture we begin a brand new section in which you will learn everything about AVL trees. So in this section you will get a deep knowledge about AVL tree, which includes why we need AVL trees, creation of AVL trees, common operations on AVL trees, balancing of AVL trees, and finally we are going to learn rotation of AVL trees. So in the first lecture let's identify what is an AVL tree. So by definition, an AVL tree is self-balancing binary search tree where difference between heights of left and right subtrees cannot be more than 1 for all nodes. So from this definition you can easily see that an AVL tree is also a type of binary search tree. This means that all properties of binary search tree are applicable for AVL trees as well. So this means that the elements that are located on the left subtree are less or equal to the root node, and the elements that are located on the right subtree are greater than the root node in this case. So these properties of the binary search tree are applicable in AVL tree as well, but in case of AVL tree we have an additional property for a binary search tree in which it says that binary search tree must be balanced. So we know that binary search tree can be balanced or disbalanced, so in case of AVL tree it cannot be disbalanced. So the AVL tree makes sure that binary search tree is balanced. So how can an AVL tree keep a binary search tree balance? So the mechanism is simple. It uses height balancing. So let's look at this example over here. So let's say we have a binary search tree like this, and we are going to check that if this binary search tree is AVL tree or not. So in this case we are going to start from the first node. So in the root node we have 70. So the height of left subtree of this node in this case is 3, because in this case from root node to the last leaf we have to go 3 steps. So this is 1, 2 and 3. And we need to find the height of right subtree. So in this case height of right subtree is 2, because from root node to the deepest node we need to go to 2 steps. So that's why the height of right subtree in this case 2. So the difference between them is 1. So this means that in this case this node confirms with the property of AVL tree, but here it says that it has to applicable for all subtrees over here. So then we are going to continue to check right subtree. So in this case also the height of left subtree is 1 and the height of right subtree is 1, so difference between them is 0. So this means that this node also confirms the property of the AVL tree. Now when we come to the left subtree, in this case when we are calculating the height of left subtree, we see that the height of left subtree is 2 and the height of right subtree in this case for this node is 0, and the difference between them is 2, which means that this node does not confirm with the property of AVL tree, which says that difference of right and left subtrees height must be at most 1, but in this case the difference is 2. So you might be interested that is there any way that we can make this node to confirm with the property of AVL tree? So the answer is yes, we can do it by rebalancing the tree. So if at any heights of left and right subtrees differ by more than 1, then the rebalancing is done to restore AVL tree property, and this process is called rotation. So we will learn how can we do rotation and detailed of information about rotations in our upcoming lecture. So for now you just need to know that whenever any node fails to follow the property of the AVL tree that we showed over here, the rotation is needed for rebalancing and to make this unbalanced binary search tree balanced. Now let's look at some examples of binary search tree and check that if they are AVL tree or not. So the first example is like this. So here to check that if this is an AVL tree or not, we have to check heights of all nodes one by one and compare their heights with left and right subtrees. Now in this case the root node is 70. Now the height of left subtrees of this root node is 2 and the height of right subtrees of this node is 2. So the difference between them 0. So this means that this node over here confirms with the property of AVL tree, in which it says that the difference between left and right subtrees height must be at most 1. So in this case it's 0, so this means that this node over here confirms with the property of the AVL tree. Now we are going to continue to the next node. So in the left subtree we have 50, in which we have 2 children, and the height of both left and right subtrees are 1 and the difference between them 0, so this means that this one also confirms with the property of the AVL tree. Then we are going to continue with the right subtree. So here again the left subtrees and the right subtrees height are 1, and this node also confirms with the property of the AVL tree. So this means that this whole binary search tree over here is AVL tree, because all subtrees over here confirms with the property of AVL tree. Now let's look at another example over here. Now here again we are going to do the same operations. So we are going to check that if root node confirms with the property of the AVL tree, then we are going to check the left subtree, then the right subtree. So we are starting from the root node. So in the root node we have 7th over here. So the height of left subtree in this case is 3, and the height of right subtree in this case is 2. So in this case the difference between the height of left subtree and the height of right subtree is 1. So that's why this confirms with the property of the AVL tree. So we are going to continue to the next node. So in the left subtree we have 50 over here. So the height of left subtree of this node is 2, and the height of right subtree of this node is 1, and the difference between them is 1. So this means that this node also over here confirms with the property of the AVL tree. So we are going to continue to the right subtree. So in the right subtree we have 90, in which we have 2 children. So in this case it's obvious that the height of left and right subtrees are 1, and the difference between them is 0. So this means that this node also confirms with the property of the AVL tree. Now at the end we have another smaller subtree over here, which is located at the left subtree. So here we are going to check this node over here. So in this case, whenever we are checking the node that confirms with the property of the AVL tree, we are checking the nodes in which we have children. So if a node has at least one child, we have to check that node to see that if that node confirms with the property of AVL tree or not. So in this case we see that for 30 we have one child, so the height of left subtree in this case 1, and the right subtree's height is 0, and the difference between them 1. So this means that this node also confirms with the property of AVL tree. So this means that this whole binary search tree over here is an AVL tree, because all nodes over here confirms with the property of AVL tree. Now let's continue to the last example. So in the last example we have a binary search tree like this. So in this case, one more time we are going to start from the root node. So the left subtree's height of this root node over here is 4, and the right subtree's height is 2, and the difference between them is 2. And in this case, this binary search tree over here is not AVL tree, because this is disbalanced binary search tree. So if we want to make it an AVL tree, it means that we have to do some rotation over here to make this binary search tree balanced binary search tree. So in that case, it's going to be an AVL tree. So with this, we have come to the end of this lecture. So in this lecture, I have explained what's an AVL tree, and we have learned that an AVL tree is a binary search tree with an additional property, and we have looked at some examples of AVL tree. So hopefully everything is clear about this lecture. Now in the next lecture, let's see why do we need AVL tree.